11. And in this lecture, we will discuss something special. What we will discuss is we will discuss only the second order ODE. And what we are interested in the second order ODE is the behavior of the solutions. In particular, what we will be discussing is something called oscillatory solution. So before we go forward, let me say something which will be useful later on. Let us consider a second order linear ODE with the so of course it's linear ODE. So let us consider a second order linear ODE, and what I will tell you is that we can how to discuss the solutions of different ODE. Okay, so let us consider second order linear ODE. So second order linear ODE, as you know, will look like this. Let's write it in a different form. Let's write it in y double prime or x double prime. Let's do it x double prime. So x double prime plus p of t x prime plus q of t x is equal to 0. Of course, it's homogeneous. Huh? Now, I want to show you a trick that I can convert this ODE into another ODE of the following form. Okay, so I'm going to convert the ODE for x into ODE for y, where you don't have first order terms. The first order term vanishes. And how to do that? And it will be clear in a second why I'm doing it. If not in a second, but in 5 minutes. So how to do that? You will substitute x t is equal to y t exponential minus half of integral of pt dt. And this pt is exactly this pt. Okay. So if you call this function as e of t, and then if you evaluate the derivative of x, evaluate the derivative of x and plug it in here in the form of y, then you will see that for y you will get a ODE for which there is no first order term. Only you will have some new q function, and this, of course, this is not equal to this one. Huh? So this is not equal to this one. It's some other function, but nevertheless there will be no first order, I think. Second important thing is that if xt naught is equal to 0, so then this implies y to t naught is equal to 0, and it's both way implication. And this is why very important that zeros of x and y are same. Okay, when I say that xt naught is 0, if and only if it will be yt naught is 0. Now let me show you this, because otherwise you might feel that something is missing. So let me try to show you this calculation at least, and then you can see that what kind of OD for y you get, and then I'll tell you why we will consider, why we are interested in this conversion. Okay. So first let us note that x of t is y of t e of t, where e of t is exponential minus integral half pt dt. Okay. So clearly what will be x prime t? This will be y prime e plus y e prime. Okay. And this I can write it is equal to y prime e minus, because now I'm going to use its derivative and take this thing out. So I'll evaluate it. So what I will get is minus half pt yt et. That is because from e prime t is nothing but minus half pt et. Okay. So now similarly, if you write x double prime, what you'll get, let us evaluate this term first. You'll get y double prime e plus, let us, because you already know what is e prime, let's directly write down the expression, minus half of pt et y prime. So this term goes here, right? Okay. Then we go to the second one, and it has three terms, so we'll use a chain rule for the three functions. So minus half p prime y e plus p y prime e minus half p y again p e. Okay, this is what we'll get. All right. Now, if you look at only the first two terms, okay, in fact, okay, let's write it completely. Then this will be, so basically I'll be multiplying this with this, sorry, with this, and adding this into this, and this will not create any derivative terms, so only these two terms has to be looked at. So now this will be, now x double prime will be basically y double prime e, that is not an issue, minus, so what are the first order terms here for y? Only that I want to point out. So the first order term for y are, one is this one is this one. So you sum them up, what you get is that minus p y prime e. Okay. If you go to the first order term, so of course there will be some more terms, but I am not concerned about that. But then you go to the first order term, this will be pt multiply with x prime, and okay, so am I making a mistake somewhere? Okay, so let's see if I made a mistake somewhere. Half of y prime et, okay, then there should be some cancellation here. Okay, so let us see, pt multiply with the first order, so this will be y prime, okay, so this is fine, y prime e, this is the only first order term we have. Okay, so this is correct. Okay, no problem, I'm not making a mistake. And this term, of course there will be some other term, but I'm not concerned about that because they don't contain the derivative for y, and this term get cancelled with this thing. So the whole thing can be written now as y double prime plus something, this something is this one, this is equal to 0. Okay, so why we are interested in this form? So now let us consider, instead of general second order linear ODE, we'll consider only this kind of ODE. Okay, and the reason to consider this kind of ODE is that we are going to be interested in the places where the solution of these ODEs vanish. So if x1 t is a solution, We are interested in zeros of t, zeros of x1. So clearly, if I don't have this form of ODE, and if I have general form of ODE, I can convert it into this form and then look for the zeros. Zeros won't change, right? Because I already told you that zeros are not changing. Zeros of this ODE and this ODEs are same. So instead of considering this thing, I'll just consider this thing. Is this point clear? If I'm interested in zeros of the solution, it's enough if I consider this kind of ODE. Is this point clear from this discussion?
Yes, sir.
Yeah. So that's why I will only look for the this kind of ODE for this discussion. And this discussion will only be important when I'm looking at the zeros of the solution. For other things, of course, it is not straightforward. But the critical point for us is that I'm interested in only zeros of the solutions. Okay, so now with that in mind, let us look at some examples. Let us look at the simplest possible thing. Okay, so this is a second order ODE of this form where I take q equal to 0. As you can see, the solutions of this ODE, whatever is the solution, of course you have to specify the initial condition to get fix one solution, but I'm talking about now all the solutions of this ODEs has maximum 1 0, right? Do you agree? Do you agree? X double prime is equal to 0 can have maximum 1 0.
Yes, sir.
I mean, it will be a linear function, right? You just integrate it twice, you'll get this implies that x t will be something like a t plus b for some constant a and b. So it can have at most 1 0. You can solve this. Okay. On the other hand, if you look at where k is positive number, can somebody tell me the zeros of the solutions? Yes, can somebody tell me zeros of the solution? For k positive.
2.
What will be the solutions for that? So what will be the general solution for this thing? C1 cos of, right, agree, lambda square plus k is equal to 0. So lambda is equal to plus minus square root of k, right? I. Agree? Square root of kt.
Yes, sir.
C2 sine of square root of kt. Okay. So you can see that the solution is fairly oscillatory, right? Depending on what is the value of C1, C2, it will have infinitely many zeros, right? Agree?
Yes, sir.
And now you can see that by only looking at the value of q, you can immediately start saying, well, when q is greater than 0, well, you will have oscillatory solutions. When q is 0, we'll have only linear solution. When q, so if you take k to be negative, then if you look at this thing, you might not have no zero solution, right? There might be not be any zero. Because you will get exponential minus kt plus kt. At most you will have 1 0, not more than that, right? Agree?
Sir, how can we have 1 0 in this case?
You will get c1 e minus square root of kt plus c2 e kt, right? Depending
Yes,
on
sir.
these values of these C1 and C2, your curve might pass through one of them.
Okay, sir.
Right, you can take C1 to C2 to be 0, and then you take yeah, or you can take something positive and C1 to be negative, then it might goes through it. But roughly speaking, you will have at most one. Okay. So now we are interested now to looking at this Q. What can we say about the solutions or behavior of the solution? We might not be able to find the solution, but we can definitely say something about the solution. So now, by looking at these examples, and I'll keep coming back to these examples whenever I need it, let us define a particular behavior of the solution. Okay, so let us consider, so that we define, consider x double prime plus qt x is equal to 0, or we can write it as pt. It doesn't matter what I write here, but let's write pt because that will be simple. Okay, then we say that a non-trivial solution. What do you mean by non-trivial solution? That means non-zero solution. Okay, not that x is equal to 0 function is always a solution, because it's a homogeneous case. So non-zero solution is oscillatory. Okay, so we say a solution is oscillatory if for any number xi or any number tau, there exists xi bigger than tau such that xi is a 0 of xt. Okay, so a non-trivial solution, let's call it xt. So let me explain why we call it oscillatory, and then it will be clear to you. So assume you have again example. So let us assume that you have a function xt and it has 0 at t0. Okay, then this, if it's oscillatory by definition, then this implies that there will be, if I take some t1 which is bigger than t0, then there exists another, let's call it xi1 bigger than t1 such that x at xi1 is 0. Now I can take another t2 bigger than xi1. Okay, if I take t2 to be bigger than xi1, then there exists xi2 bigger than t2 such that x of xi2 is 0. The point is that you have infinitely many solutions, infinitely many zeros, right? This implies that x has infinitely many zeros. Okay. Of course, here I am assuming that I am considering this on whole R, right? I'm considering this ODE on whole R, and if P happens to be continuous on whole R, then you will have existence and uniqueness for the initial value problem. But here we don't have initial value problem, so you will have existence of the general solutions. Okay, so the point is that X is oscillatory as it has infinitely many zeros. Okay. Exactly the case if you look at x double prime plus x is equal to 0. You can take any solution. Okay. For example, the one solution will be sine t. Of course, it's oscillatory, right? Agree? Agree? This is oscillatory.
Yes, sir.
Yes, sir.
You take any other you can take is to be cos t. You can take it to be sine t plus cos t. Okay. You can take 2 sine t plus 10,000 cos t. All of them are example of oscillatory functions. Okay. Now, another interesting question which we'll try to address now is that what is the relation between the zeros of this thing? So is the definition of first thing, is the definition of oscillatory solution clear to you? Is it clear when we say a solution is oscillatory?
Yes, sir.
Yes, sir.
So it has to have infinitely many zeros, and those zeros of course will converge to infinity. That we will prove in the end, but for the time we are not proving it, but we will come back to it later. Now what we'll do now is that we'll fix OD, this OD, and we'll try to find the relation between zeros of different solutions. So if, for example, if I know what is zeros of this, what can I say about zeros of this? If I know the zeros of this, what can I say zeros of this? If I know zeros of this, what can I say zeros of this? Okay. Not that this is a simple ODE, I know the exact solution, but in general, given on the P, you might not have a very nice expression for it, so it's not a trivial discussion. Okay. So in that context, we have we will do something called Sturm separation theorems. Okay. So the first thing what we'll do is Sturm separation theorem. Yeah. Okay. And it's not a very hard theorem if you go back to this test case, this example. So if you look at only first two things, sine t, cos t, and let me try to plot the graph for both of them. So this is my t axis, and of course sine will go like this, and cos will go yeah. My drawing is horrible, but you get the idea, right? Yeah. Sine pi, okay. So something like this. Okay. Something like this. Maybe not cos t, then minus cos t. It doesn't matter. Okay. So then what you see? Immediately you'll see that between any two zeros of sine t, there is a zero of cos t. Agree? Do you agree? What are the zeros of sine? 0, pi, 2 pi, 3 pi, 4 pi, right? What are zeros of cos t? Pi by 2, 3 pi by 2, 5 pi by 2, and so on and so forth. So between any two zeros of sine, there is exactly one zero of cos. Agree?
Yes, sir.
Okay. Now, can we make a similar general statement for any two different solutions? Can I say that between any two zeros of this function, there will be 1 0 of sign, exactly 1 0. Okay, or any of these things. And what will be the criteria to select between them? Okay, and this is exactly done by the separation theorem. So let x1 t and x2 t are two linearly independent solutions of x double prime plus pt x is equal to 0. And suppose A and B are two consecutive 0. Zeros of x1. That is xa is equal to xb is equal to 0 and xt is not equal to 0 for any t lie between a and b. This is what I mean by conjugative 0, right? That there is no other 0 in between. Sorry, x1. Okay. Then x2 t has exactly 1 0 in the interval AB. Okay, this is what we are going to prove, and it's exactly like saying that between two zeros of sine there is exactly 1 0 of cos and vice versa. Okay, but now we are going to prove this for the general solutions. So we take two linearly independent solution. If one of has two zeros, let's say at AB, and there is of course no other 0 in between, then x2 will have exactly 1 0 here. So what it says that if x1 and x2 are linearly independent, if x1 vanishes at 2 points, then x2 also has to vanish. It cannot be, independent. It cannot not vanish. It has to vanish between these two zeros. Okay, and the implications of this result will be discussed later on. Let us look at the proof first. Okay. Now assume, okay, it should be very clear that x2a is not equal to 0, and of course this is also not equal to x2b. Why? Can somebody tell me why this is not, this will be the case, that x2 will not vanish at a and b? Can somebody tell me why x2 will not vanish at a and b?
Sir, because they're linearly independent.
Yes, exactly. So if x2 vanishes at a, then Wronskian at a of x1, x2 will be 0. Similarly, if x2 vanishes at b, then Wronskian of x1 and x2 at b is 0. And if Wronskian is 0 at one point, it will be 0 everywhere. Not that they are the solution of a second order linear ODE. Okay. So this cannot happen. Okay. Otherwise, Wronskian at t equal to a or t equal to b will vanish, which will imply that x1 and x2 are linearly independent. Contradiction. So clearly this will not happen. Now suppose x2 does not vanish for all t in open interval AB. Okay, and we are going to get contradiction for this point. Suppose this is true, then consider a function ht which is x1t by x2t. Of course, if there is no 0 of x2t, x2 in AB, this function is well defined. Okay, is well defined function on AB. Okay, not only that, also h of A is 0 is equal to h of P. Because x1 of A is 0 and x1 of B is 0 and x2 of A is not 0 and x2 of B is not 0. So this will happen. So this implies by Rolle's theorem there exists C in open interval AB such that h prime C is equal to 0. Okay. This implies what is h prime? H prime C is x2C, x1 prime C minus x2 prime C, x1C divided by x2 square C equal to 0. Now, this is never equal to 0, so this will be 0. So this implies x2 C, let's not write it in this form now. x2 x1 prime minus x1 x2 prime evaluated at C is equal to 0. This implies that what? What does this imply? What does this imply?
Wronskian is 0.
Exactly. This implies Wronskian at C is 0. This is implies that x1 and x2 are linearly dependent, which is a contradiction. So this cannot happen. So there exists a T in open interval AB such that what happens? Such that x2t is equal to 0. Immediate consequence of this result, and this is actually a pretty old result, it's some 1836. This is from 1836 by Strom. Okay. So immediate consequence of this result is that corollary, which says that if x prime pt x is equal to 0 has one oscillatory solution, then all other solutions are also oscillatory. Okay. Why? You take any other solution, either it's linearly dependent or linearly independent. Right? There are only two linearly independent solutions for the second order. If it's linearly dependent, then it has exactly the same 0. If it's linearly independent, then it has 0 between two conjugative zeros of that thing. So of course, if the first one has infinitely many 0, other one will have to have infinitely many 0. Okay. So this is trivial. It's just observation. Is this part clear? Is this part clear?
Yes, sir.
Okay. So now you can immediately see what is the consequences of this thing. Now I don't need to know anything about these functions what I shown you, other than that they are the solution of one ODE, 1 second order ODE. Then I can always say that this function, although I have no idea what the hell this is, has a exactly 1 0 between 0 and pi. Similarly, whatever that function, you can take any linear combination sine and cos, that will have exactly 1 0 between 0 and pi. Exactly 1 0 between pi by 2 and 3 pi by 2. And so on and so forth. Okay. So by just looking at the zeros of a simple thing, you can get zeros of the fairly complicated function. Okay. And this is not restricted to this constant coefficient. This statement is about general P. So if you can get a one oscillatory solution for this thing, all other solution will be oscillatory, and you'll know where their zeros are, at least in interval. In some interval, you know what their zeros will be. Okay. Now still, this is a very impressive theorem, but still you understand that it's even impossible to get one solution sometimes. So the question is that, can we just look at this function P, or as I explained you here Q, corresponding to this discussion, and say that whether the solution will be oscillatory or not. Okay. And that is the next theorem what we are going to do. What we are going to do is that we look at two ODEs and then decide how their solutions will behave. Okay. So this is called Sturm comparison theorem. Why it's comparison theorem? Because we look at two ODEs, not one ODE. Okay. So we consider two equations. Okay. X prime plus pt x is equal to 0. The second equation is y prime qt y equal to 0. Assume x is a non-trivial solution of, let's call it 1, this is called, let's call it 2, solution of 1 with conjugative 0 at t equal to a and t equal to b. Okay. Then okay, so the setting is exactly for the first case, the setting is exactly like in the first theorem before it. We also need to assume some relation between P and Q because we are going to compare them. Okay. So furthermore, assume that P and Q are continuous on closed interval AB. Okay. And PT is strictly less than equal to Qt. Not strictly less than, but it can be equal at some point. But with strict inequality holding at least at a point. Let's call it T star in A, B. So there exists at least one T star where you have strict inequality. Of course, in general, PT will be less than equal to QT, but at least at one point it will be Q will be bigger than, strictly bigger than P. Now, if YT is a non-trivial solution of 2, such that y of A is equal to 0, then there exists C in open interval AB such that yc equal to 0. Okay, so let me explain this with the example. So we consider two ODE. One is x double prime plus x is equal to 0. Consider y double prime plus 2y is equal to 0. Solution of this ODE will oscillate faster than this ODE. Agree? Do you agree? For example, the solution for this will be at least one solution will be sine t, and one solution for this will be sine square root of t. Okay, clearly sine square root of t oscillate faster than the sine of t, because if you plot, and let us say this is t equal to 0, then okay, so this will be graph of xt, but graph of yt will be basically something like this, right? Because it will be at pi by root 2, it will vanish here, right? So this is our A here in the discussion. This is our A, this is our B. So note that x at A and y at A both are 0, but because this coefficient for y is bigger, it will vanish before another 0 of x itself. Is this description clear to you?
Yes, sir.
You are able to follow, right? What happens if the higher the coefficient, faster the oscillations. Okay, and this is what we are going to prove for the general case. This term is bigger than this term, and there is at least one point where it's strictly bigger. That's why you get in open interval AB. Okay, otherwise you might not get an open interval AB. You might have to close it if you just don't assume that. Okay, but because of this strict inequality at one point, the oscillation will be faster here, so it has to vanish before the other one. Okay, now nowhere I am saying anything about the oscillatory solutions here, but clearly you can see that if x has an oscillatory solution, the first ODE has oscillatory solution, this second one will obviously have oscillatory solution. Okay, by just looking at this function, because the solution of this has to vanish between two zeros of this thing. So that is very clear. It might, this might have more than one zero between, but definitely there will be at least one. Right? It might have more than one. For example, if I put here 5, then it will vanish, it will oscillate very fast. So you might have more than one, but you will definitely have one. Okay, and this is what we are going to prove in the next class. Okay, so this will be proof in the next class. So I'll write it here, lecture 12. Okay, so that we can just go through it very fast. All right, so with this I stop the recording and I'm open to take your questions.